Ideal filters frequency response. Now let us see the ideal response of different filters. Here FL indicates the lower cutoff frequency and FH indicates the higher cutoff frequency. Ideal characteristics of low-pass filter. This response shows that the low-pass filter will allow the signals up to lower cutoff frequency and stops the frequencies higher than the lower cutoff frequency. Ideal characteristics of high-pass filter. This shows the high-pass filter will allow the frequencies greater than the higher cutoff frequency and stops the frequencies lesser than the high cutoff frequency. Ideal characteristics of band-pass filter. This response shows that the band-pass filter will pass the frequencies between the lower cutoff region and higher cutoff region only. It stops the frequencies which are lesser than the lower cutoff frequency and also stops the frequencies greater than higher cutoff frequencies. Ideal characteristics of band-stop filter. The above figure shows that the frequencies which are greater than the lower cutoff frequency and the frequencies which are lower than the higher cutoff frequency are not processed. Capacitive reactance. When the resistor is connected in series with the capacitor forms RC circuit. In RC circuit the capacitor will charge from the D.C supply voltage, and when supply voltage is decreased, eventually the capacitor also discharges by reducing its storage charge. Not only at the time of the D.C supply, even in the case of A.C supply also according to the supply voltage level the capacitor will charge and discharge continually. But due to internal resistance there will be some attenuation in the flow of the current through the capacitor. This internal resistance is called as capacitive reactance. X_C indicates the capacitive reactance and it is measured in ohms, same as that of the resistance. When the frequency is varied in the capacitive circuit according to the amount of frequency change, this capacitive reactance value also changes. The electrons flow from one plate to the other plate causes the current flow in the circuit. But due to the movement of electrons the frequency level varies. When the frequency through the capacitor increases the capacitive reactance value decreases, and when frequency through the capacitor decreases the capacitive reactance value increases. Thus, by this we can say that the capacitive reactance is inversely proportional to the applied frequency level. This shows that the capacitor connected in the circuit is dependent on supply frequency. This phenomenon is called complex impedance. Capacitive reactance formula. Xc equals 1/2 pi 1c. Where Xc equals capacitive reactance. Pi equals 3.142. F equals frequency in Hertz. C equals capacitance in farads, F. Capacitive reactance example. Let us consider two frequencies to observe the capacitive reactance phenomenon. Let f_1 equals 1 kHz and f_2 equals 10 kHz and the capacitor C equals 220 Nf. At first frequency level, x_C equals 1/2 pi f1c equals 723.4. At second frequency level, x_C equals 1/2 pi f2c equals 72.34. This shows clearly that with the increase of frequency the reactance decreases. Capacitive reactance vs frequency. From the above frequency versus capacitive reactance plot we can observe that when the frequency is 0 the reactance value reaches to infinity. This shows the phenomenon of the open circuit. When the value of the frequency increases exponentially the reactance value decreases. When frequency reaches to infinity the reactance value at nearly 0. This gives us closed circuit behavior.